faculty from Korea University. They sent our research title Development of 3D Textile Electrodes for Electrocardiography Measurements. With the growing importance of wearable healthcare monitoring in aging society, continuous and accurate biosignal acquisition, particularly electrocardiography, has become more essential for early diagnosis and personalized healthcare. But conventional AGAG-cell wet electrodes has faced several limitations such as gel drying or poor breathability and skin irritation during long-term use. Textile-based dry electrodes can provide a better flexibility and comfort, but often suffer from high impedance and unstable skin contact. So, to address these challenges, we proposed 3D embroidery-based textile electrodes that with a polydimethylsiloxane substrates that aiming for stable skin contact and low impedance biosignal acquisitions. The fabrication process was begun with a silver-coated polyamide thread, and the 3 cm circular pattern was designed using ink-stitch software. And PDMS substrates were prepared with a 100 to 11 curing ratio and cast into 5 by 5 centimeters molds, and then degassed for 2 hours, and finally curing at 40 degrees for 1 day. After curing, the conductive threads were embroidered directly onto the PDMS substrates with a computerized embroidery system. So 2 types of electrodes were fabricated. First one is 3D planar electrodes, and the second one is flat electrodes that representing conventional textile electrodes for comparison. An ECG measurement was conducted using BioBrain biosignal acquisition systems in a sampling rate of 250 Hz. A standard lead 1 configuration was applied with AGAG reference electrodes. And prior to ECG measurements, the skin electrode impedance was evaluated up over 10 to 10 kHz frequency range in a bipolar setup. ECG signals was recorded for 3 minutes under 2 conditions. Static conditions that representing a resting state, and a dynamic condition involving repeated C2 stand motion for assess robustness against movements. And our signals were processed using 6 Hz notch filter and 0.5 to 30 Hz bandpass filter. Then RPICs were detected, signal-to-noise ratio, and correlation with individual heartbeats with AGAG reference electrodes were analyzed. So this slide compares skin electrode impedance and mean ECG waveform quality from 2 electrode types. The 3D planar electrodes exhibited consistently lower impedance across entire range of frequency, and especially at 10 Hz, the skin electrode impedance was reduced approximately 80%. And in ECG measurements, the 3D planar electrodes can provide a clear PQRST morphology closely resembling an ideal ECG waveform. And we further evaluated the signal quality using signal-to-noise ratio and correlation analysis. So the 3D planar electrodes achieved a higher SNR, demonstrating the signals that improved signal stability and reduced motion artifacts. And in correlation analysis, the 3D planar electrodes reached a 0.85 correlation. So it's confirming that the 3D structure can effectively reduce the motion artifacts with daily movements. So in conclusion, we proposed a 3D embroidery-based textile electrodes that integrated with PDMS substrates, which reduced skin electrode impedance and enhanced the ECG signal clarity. We further required the validation of actual contact area with the skin and pressure distribution or diverse 3D geometric of 3D structures. So as the future work, we explored the diverse 3D geometries by redesigned our molds, and we applied the porous PDMS structures for enhanced electrodes breathability and flexibility. And even, thank you for your attention.